Okay, good morning, everyone. I want to wrap up node voltage analysis today and then introduce the topic of mesh current analysis. Quick couple of notes or a couple of points. The homework for node voltage analysis was, well, I made it due on Saturday, but I have one last slide to cover. So I'm going to push it back to Sunday. Okay. But that still doesn't, I mean, it's only 3 problems, so you shouldn't have any issues with that. Mesh current analysis, I will introduce the topic today. We'll look at the examples and some of the theory. So I would expect students to actually open up the next homework and actually take a look at it. And then we'll try to finish it Monday and then possibly Wednesday. So the homework for mesh current would be assigned perhaps Thursday or Friday of next week. But again, we have few days in the in between after Monday. So I would expect students to open it up and start working on it as much as they can. Second point about homework is I want to address one of the comments I received in the feedback. It said that there were some topics on one of the problems that were not talked about in class. And when I looked at it, it says about the extra credit problems. So again, as a reminder, again, I have no idea which student left that comment, obviously, but I'm here to address it. So at the beginning of the class and in the syllabus, I described that this is a multimodal, multi-level class. The multimodal, of course, describe the modes, which is in-person, online, or asynchronous. The multi-level is basically if students want to do remedial work, then you have some background from the preceding topics. And then more importantly, if there are some students who wish to delve into the subject a little bit deeper and want to go beyond what is the normal scope of the syllabus, then they can do so in the practice problems and in the extra credit tutorials. So the tutorials that are on there will, on occasion, have certain topics that are beyond the scope of this class. And the purpose of that is, of course, some students like to do that extra work, and hence the extra credit. Okay? And so that's the point I wanted to address. So if you see an unknown topic in the actual homework problem, meaning which is not an extra credit, then yes, I would make sure that that shouldn't be the case, because anything that's in the homework it's either an extension of what we talked about in class, or it's a topic that's covered in detail. But the extra credit tutorials and the video solutions, they might be referring to a topic that is beyond the scope of the normal syllabus. Again, that is just so that students can work on the topic at a different level. Okay. It's optional. If you want to do it, you do it. If you don't want to do it, then you don't. But again, it's optional. It's extra work, and hence the extra credit. Okay. Yes. Did anyone have a question? Okay, no questions. Then let's pick up with our analysis topic. Section 04. All right, so we did this example last class and we stopped. I mean, we're done with this example, but I just wanted to reiterate the point that no matter which node we pick as a reference node in a node voltage analysis solution, we will still end up with the right answer. Okay. So in this case, if A was my reference, I would have VA as 0. If B was my reference node, then VB would be 0 volts. And then VA would be what, approximately 39 point some volts. And VC would be 52.857 volts. Okay. Your answer would not be incorrect. Your answer would be correct when I take it in conjunction with the reference node. All right. So my VA here would be plus 39. So it looks like a different number, but just because when I'm measuring A, here I'm measuring with respect to C. If I measure A with respect to B, that difference will still remain the same. And that's the point. You can choose any node in the circuit as your reference node. It doesn't have to be that specific node. Okay. So that's the reason I choose C, because I can show that the voltages are negative, but does not mean that your answers are incorrect. Once we have these, I talked about how we can plug it into the equations here and here to find the resistor voltages VR1, VR23, and VR4, right? So you plug these values back, and I would get VR1 is equal to VA minus VC, VR23 would be VA minus VB, IR1 would of course be VR1 divided by R1, and IR23 would be VR23 divided by R23. So once you have your node voltages, again, node voltages are with reference to a certain point in the circuit. You can plug those values back into the circuit and find all the other resistor voltages, and you apply Ohm's law, you find all the other resistor currents. Okay. And that's the point of this technique. Make sense? Any questions? Any questions at all? Okay. All right. Then let's move the concept of supernode. What do we do when you have a voltage source in the circuit and you cannot describe that current by any means possible? Okay. At first glance, this looks like a very complicated circuit. Or, well, not complicated, but surely that you'd have to write a lot of equations. Or what if I tell you that you only need to write one equation to solve the circuit? And that's it. You only need one. So let me prove it. All right. So we have voltage sources, 10 volts and 15 volts, right? 10 volts and 15 volts. Now each resistor current I can describe in terms of Ohm's law. Right? You simply take the resistor voltage divided by the resistance, and you can describe whatever resistor current you have. But we cannot do the same for a voltage source, right? I could have this voltage source as, I don't know, IS1. I could have the current going through here as IS2. But then what? I have my variable, but it's an unknown variable. I cannot write an expression for IS1 or IS2, right? So if I cannot write it, then I would just get rid of it. And that's where the supernode concept comes into the picture. Supernode concept allows me, well, not allows me, but it permits us to write an expression directly by skipping certain steps. So it's, in a way, it's similar to the voltage division and the current division principle. They are derived from Ohm's law, voltage and current division. They are derived directly from Ohm's law. But if you apply those principles directly, it allows you to skip one or two steps. And it's the same kind of concept here. Okay. If we take a look at, let's say, the 15-volt source, okay? If I want to apply a supernode, what we do is we take the source out and we replace it with a wire. And thus we combine both ends of that voltage source into one single node. And then we write our equation or KCL at that supernode. And that's the concept of supernode. we take that voltage source out and we replace it with a short right here. We replace it with a short only for that one step. That's it. Only for that one step. This is to enable us to write that one single equation. Now, typically, I don't do the derivation for supernode in a non-EE class, again, because we again don't go deep into the derivation. It's good to understand things, obviously, but as non-EE majors, it's more important for you to understand how it works. I mean, not how it works, how to use it to solve problems, okay, how to apply the techniques. So let's take a look at the supernode right here, 15 volts. Now, as I was saying, typically I don't do it, but the first section today, students had questions, and so I went into the derivation. And I did the same for the second one, so we'll do the same for here also. So this is the circuit. You have a voltage source, and we are not worried about the reference source just yet. Okay. This is R1, R3, R4, and R2. Assume current direction, IR1, IR3, IR4, and IR2. I'm going to call this, since I labeled it IS1, I'll stick with IS1. Okay. And then I will label these nodes right here as X and the bottom node as Y. Okay. So this is just the circuit setup, the beginning of the setup. So now we can write an expression for IR1, 2, 3, 4, right? Easy enough to do that from Ohm's law. Actually, just wait until students finish writing it down. Okay. All right, so let's apply KCL at X. Again, this derivation is not important. It's more important that you understand how it comes. So you don't have to write it down if you don't want to. So you apply KCL at X. What do I have? I have two currents entering. IR1, IR3 entering the junction, and IS1 leaving. So I have IR1 plus IR3 equal to IS1. KCL at Y. I have two currents entering. Sorry, not two currents. One current entering and two leaving. So I had, wait. So IR1. Oh, I had IR4 coming down. Just a second. IR4 was coming down. It actually does not matter which direction you choose, but for the previous two sections, I chose it coming down. So at IR4 plus IS1 equals IR2. Now, if A equals X and B equals X, well, not this X, but let's say A equals Z and B equals Z, then automatically it follows that A equals B. So you rearrange the terms, you get expression for IS1. So this one, the second expression becomes IS1 is equal to IR2 minus IR4. And from these two, I can equate and I can write IR1 plus IR3 equals IR2 minus IR4, thus getting rid of or eliminating IS1 from my equations. So the unknown equation is gone, or the unknown variable is gone. Does that make sense? Let's take a 10-second pause. You think over it. Let me know if you have any questions. Right? KCL at one end of the voltage source, KCL at the other end of the voltage source. You assign a random variable to that current. Once you apply KCL, you have that random current, the random variable equals to the currents entering the junction. At the other end, they are leaving the junction. Equate both of them and you obtain this expression, which is the exact same expression you would obtain if you combine this into a supernode. So if I combine it into a supernode, around 15-volt source would give me remember, this is the exact same node. All are wires. As long as there are wires, it's the same node. So current entering, current entering, current entering, and one current leaving. IR2 would again be equal to IR1, IR3, and IR4. So when I have a supernode, I can apply KCL around that supernode. And I can obtain IR2 is equal to IR1 plus IR3 plus IR4, which is the exact same equation as this one. Ten-second pause. Think over it. Let me know if you have any questions. Yes. When you have a voltage source. If you have a voltage source and you want to write more equations, if you need to, that's when you would use it. And the point of using it is so that we don't have to write KCL equations at the other two ends of the node. So we can eliminate all of this work. It's a shortcut. In the name of efficiency, we don't have to do all those multiple steps. We can directly write that equation. All right, does that make sense to everyone? Any questions at all? Now, students don't have to do the supernode. Okay, you can simply apply KCL and work through the longer way if you want to. I'm not going to test students on how to, on the specific application of a supernode. All right. So then let's look at the problem. I mean, I'm not going to solve the entire problem. This was just to illustrate the concept of a supernode. Remember, I said at the beginning, we have 4 nodes, 4 unknown variables, and I said we only have to write one equation. Let's look at it. If you have multiple voltage sources in the circuit, it actually makes your job easier. If we choose 4 as our reference, so this is 1, 2, 3, and the bottom node is 4. 4 is the reference. So I can write V4 is equal to 0 volts. If V4 is 0 volts, V3 is minus 15. And if you look at the other voltage source, it is connected between V1 and V2. It is connected between V1 and V2. Negative end is connected to V1, positive is connected to V2. Automatically, it forces V2 or node 2 to be 10 volts higher than V1. Does everybody see that? So I can write a relationship between 1 and 2 as V1, no, sorry, 2 is higher, right? So I can write V2 minus V1 is equal to 10 volts. Then I can rearrange the terms so it describes V2 as V1 plus 10 volts, or I can write V1 is equal to V2 minus 10 volts. Thus, I can eliminate one more variable. So I only need to write one equation. If I plug in these values into this KCL expression right here, I can write IR2 is going up top. This is 1, this is 2, this is 3, and this is 4. I can write IR2 is equal to V1 minus V4 divided by R1. IR1 is, no wait, IR1 is at the top, so that is V1 minus V3 divided by R1. This is R2. Yeah, that's R2. IR3 is V2 minus V3. Again, those relationships depend on the direction of the currents, okay? So V1 minus V3, V2 minus V3, that's because of the assumed direction of the currents. And this would be divided by R3 plus IR4 would be V2 minus V4 divided by R4. So now look at it. This is Ohm's law, obviously. V4 is equal to 0 volts. V2 can be described as V1 plus 10. And V3 is minus 15. The only unknown variable left in that equation is V1. And that's it. You solve this equation, you will get V1 equals, well, some value. You add 10 volts to it, you get V2. That's it. You have V1, V2, V3, V4. As I said, it's a one equation problem. So when you look at a problem, if you see more than one voltage source, more likely than not, it is much simpler than what you would expect. Just because we are applying KCL. Once you apply KCL, we express every single current in terms of the node voltages. So if you have a voltage source, you automatically have an answer for one of the node voltages, and you can describe a relationship between the other nodes of the other voltage source, which is V1 and V2 in this case. Makes things easier. You have a question? Yes, yeah, those will always be given. Yeah. Yes. So the question being asked is, can we do this for the other voltage source? The answer is yes. You can choose, for instance, we could choose, or not, one or two as a reference node. So in that case, V1 would be 0 or V2 would be 0. And then you would still solve the circuit that way. I always tell students, you can, since you can solve these circuits using multiple reference sources, if you already have the right answer, you already know your work is correct. As practice, just choose a different reference node, choose different direction of current. There are multiple possibilities. Okay, you have 4 nodes in there. That's 4 different possibilities just for reference node. And then you have 4 different currents in there. If you form a matrix of different directions for the currents, each single problem can be solved like 10 different ways or more than 10 different ways, depending on the amount of components in there. I don't expect students to do that, obviously, but solve it like 2 or 3 different ways, and then that's just good practice. That's all. All right, any questions? Does this make sense?
Yeah, I have a question.
Yes, go ahead.
How do you determine which number to subtract from which, like V4 minus V1 or V1 minus V4?
That depends on the direction of the current that we chose at the beginning of our analysis. So in this case, if I choose the currents, IR2 is going up from the bottom, right? Actually, you brought up a very good point, because here I made an error. If I choose IR2 as going up from the bottom, then IR2 will cause a polarity in this direction. And so this equation would be incorrect. This should be V4 minus V1.
So we use the passive reference configuration, and then the
Yes.
first number is the positive and the second number is the negative?
Yes, always.
Okay.
So glad that you brought up that question, because I can rectify that right now. So my assumed direction for IR2 is going up from the bottom. Passive reference configuration, of course, states that current always goes from high to low for a resistor, meaning point of entry is always plus, point of exit is minus. And so from there, it follows that my VR2, voltage across resistor R2, should be V4 minus V1 and not V1 minus V4. So everything in this case, my variables, everything was correct, except I made an error in writing out the node voltage current in terms of the node voltages, because my current direction is chosen as going up and not down. Everything else, let's see, seems correct, because this current is going left to right. This one is also going left to right. And this one is also going from 2 to 4. It's only this one that goes from 4 to 1. Okay, so that's a good case to remember. So whichever node is traveling first, like it's going in direction from node A to node B, then it would be VA minus VB. Does that make sense to everyone? All right, any questions? Any questions at all? So again, supernode is a concept. It's a, to describe in the simplest of terms, it's a shortcut. It allows us to skip a few steps. But the rest of the analysis remains exactly the same. That doesn't change. Okay. All right. So if there are no more questions, I'm going to say node voltage analysis is completely covered in class. Students should have already begun working on it. There's 3 problems on there. And right now, the homework deadline was Saturday. I'm going to push it back to Sunday. Mesh current, I will introduce mesh current right now. So I would expect students to actually at least open up the homework and take a look at it. Similar to the NVA homework, it has 3 problems. You may not be able to solve it currently, but at least open it up, take a look at it, and maybe work through the free, extra credit tutorials if you wish. So that way, there shouldn't be any surprises when the due date is, right after the class next week. Okay, mesh current analysis. Similar to node voltage analysis, we make certain assumptions. The first and absolute first thing you should note is that mesh currents are purely hypothetical. They are purely hypothetical or theoretical, if you want to call it that, hypothetical or theoretical. They do not exist in real life. They do not have a physical basis, not in the sense that we have a physical basis for an actual electric current. Okay. So first step is to identify all the meshes in the circuit. A mesh is a simple electrical loop. In this case, M1, M2, and M3. Now, our brains can automatically identify all the meshes because it's simply a simple closed loop. But an actual electrical loop can have multiple loops inside it. So a mesh is simply an electrical loop that does not have any other loop inside it. So as just a side exercise, how many loops do we see here? Let's count. So we identified the 3. So I got 1, 2, and 3, right? 3 meshes, 3 loops. Remember, a loop is any pathway in a circuit which allows you to come back to your starting point. So this is 4. 4 contains 1 and 3 inside it. This is 5. When I say this is 4 and this is 5, there is no order to it. It's random, okay? I'm just assigning random numbers to it. This is 3. 5 contains 3 and 2 inside it. And then 1 and 2. So this would be 6. And then the outer loop. 3 plus 1 plus 2. I want to call it 7. So there are 7 electrical loops. You could apply KVL to any of these 7 loops and it will still hold true. Sum of voltages around that electrical loop will always be equal to 0. So again, identifying electrical loops is not, it's important, but it's not something that we need for any analysis technique, except for perhaps KVL. So again, electrical loop is any closed electrical pathway that allows you to return to the exact same starting point in the circuit. And a mesh is a simple electrical loop that does not contain any other loops inside it. In this case, 1, 2, and 3 are simple loops. So they are all meshes. And I label them M1, M2, and M3. And after that, the next step is assigning mesh currents to each individual mesh. Those mesh currents could be rotating clockwise or counterclockwise. You choose which direction to assume. Similar to our node voltages and similar to choosing a reference node, there is no right or wrong answer. You can choose clockwise, you can choose counterclockwise. You will always end up with the right answer at the end of your analysis. Yes. Mesh is a simple loop, and a simple loop means a loop that does not contain any other loop inside it. So 4, 5, 6, 7 are not meshes because they contain other loops inside, right? For instance, loop number 4 contains 1 and 3 inside it. And so it's not a mesh. Same thing with 5, 6, and 7. Okay. All right. So as I was saying, you assume a clockwise or counterclockwise direction for your mesh current. By the way, that's my acronym for current, CCT. For a mesh current. Again, similar to reference nodes, you can choose whichever direction you want. So how do we generate equations? Well, we apply KVL. So for the node voltage analysis, we apply the current law, Kirchhoff's current law. For the mesh current analysis, we apply Kirchhoff's voltage law, KVL. Logical reasoning. Current flowing through a resistor is going to cause a voltage drop. You add up those voltages and you solve for the mesh current. Hence KVL. So let's look at mesh 1. Mesh 1 has voltage source VA R2 is here. I'm gonna draw it a little off. And this is R3. Then I have my mesh current. I1. But if your resistor is shared between two meshes, now you have two mesh currents to account for. So if you look at R2, R2 is shared between 1 and 3. You have I1 as the primary current, and you have I3 from mesh 3. You also have I2 from mesh 2. So what do we see? We see two currents flowing through a circuit. They do not have a basis. They do not have a physical basis. You cannot have two currents flowing in a circuit, whether in the same direction or the opposite direction. Two currents in the same branch of the circuit. Let me put it that way. Remember, current only flows because there is a difference in potential between 2 points. If both points are exactly the same potential, if both of them were at 100 volts, Doesn't matter. It's 100 volts, 10 volts, 0 volts. No current can flow through. Current will only flow through if one point is higher than the other. So if point A goes higher than B, then my current goes from A to B. If point B goes higher than A, my current goes from B to A, right? So current needs a difference in potential between 2 points. So you cannot have more than one current flowing through a single branch of circuit. Hence, important point to remember, the I1, I2, and I3 do not exist in real life. They are hypothetical, they are theoretical, only for the purposes of analysis. But when we write equations, we need to account for the voltage drop that will occur because of these mesh currents. And the voltage drop has a polarity that follows from the assumption we make for the direction of our mesh current. Again, remember I said at the beginning, it does not matter what we choose as the direction. We can choose a clockwise direction or counterclockwise direction, but point of entry is positive, is plus, point of exit is minus. In this case, I1 causes a voltage drop for R2 in this direction. Plus on the left, which is the point of entry, minus on the right, which is the point of exit. Then again, I3 is entering R2 from the right. So the voltage drop is plus there and minus here. Does that make sense to everyone? It is not real. You cannot have two voltage polarities at the same point. Physically impossible. Polarity exists only because one point is higher than the other. You cannot have, especially in the opposite direction. There's just no physical basis. For R3, I1 enters from the top. So we have a plus at top and minus at the bottom. And I2 enters from the bottom. And so it's plus at the bottom and minus up top. Okay. Take a 10-second pause while you think over that and let me know if you have any questions. Important topic, guaranteed on the final exam, both node voltage and mesh current. By the way, this is the last topic, last analysis technique for chapter 2. The 3 topics remaining, super important, but they simply take these techniques, you simply take these techniques and apply to those theorems. So if you have not yet looked at the final exam page on Canvas, go ahead and do so. The first problem itself will be a 30-point problem, which would run about 3 or 4 pages long. But it combines, it'll test pretty much everything we've learned so far in chapters 1 and 2. Okay, the final exam page has been up there since the beginning of the quarter. Look at the options available to you and also look at the topics. This is one of those. All right, coming back to this example. Is this clear to everyone? Any questions? Any questions at all? So how do we sum these up? Well, you sum these up as if they were independent voltages. So I would write a KVL around the loop. And again, KVL, my technique is to add up the voltages in a clockwise direction, right? You can choose your own technique if you're comfortable with it. You do not have to use mine. Oh. All right, so applying KVL, I have minus VA. Again, because if I'm adding the voltage in a clockwise direction, minus sign comes first. So I minus VA plus. Now the voltage for R, what is it? R2. Voltage for R2 is in 2 parts. One is because of I1 The other one is because of I3. And so I can write I1 plus I1 times R2 and minus I3 times R2. Both of these come under the voltage for resistor R2. And this would be plus I1 times R3 minus I2 times R3. And both of these describe the voltage for resistor R3. And this would, of course, all be equal to 0. KVL, sum of voltages around an electrical loop is always equal to 0. It always fascinates me how you can apply KVL to any electrical loop and it turns out to be 0. After all these years, it still fascinates me. Anyway, so again, if you look at some books, you won't even see this step. Okay, this is just to make students understand where that plus and minus sign comes from. Everybody understands this, right? We are writing out two hypothetical voltages for each resistor voltage. Right? Any questions on this? I would take this one step further and make a side note.
I have a question, Professor.
Yes, go ahead.
Is it normally convention to have an increase in voltage negative in our equations? And what I mean by that is for I1, if you go from like the negative terminal to the positive terminal of VA, wouldn't you technically be going up in voltage? I know like the negative cancels because you just multiply the left and right by negative, but is that convention when we do the math?
So you're saying current direction for the mesh current I1 with respect to the voltage source VA? Am I understanding you correctly?
Yes, sir.
No, that doesn't matter. So mesh current is independent of the actual currents flowing in the circuit. I could choose I1 as clockwise, like this. So I would have, let's say, VA is plus minus like this. And I could choose my mesh current going this way. And it would not matter for the purposes of the analysis, because the mesh current is only affecting the resistors. It is not affecting any voltage sources, nor any current source in the circuit. So it doesn't really matter. Okay, similar to the node voltage analysis problem, we can have a current variable assigned to a voltage source, but it does not matter because we're not going to do anything with that variable. So in this case, a mesh current I1, I2, and I3 does not affect the voltage source or the current source present in the circuit. Does that answer your question?
I was more referring to like the math, as in like if you were to follow the current of I1 in clockwise, you'd be going from the negative to the positive terminal of VA. So it'd be technically like a positive voltage, like a jump in voltage.
No,
but
that's KVL. That has nothing to do with I1 though. KVL direction is different. If I was to apply my KVL in this direction, I would have plus VA. So let's see. KVL in this would be counterclockwise direction. So it would be plus VA minus I1 times R3 plus I2 times R3, then minus I1 times R2 plus I3 times R2 equal to 0. Still exact same equation, no difference. That is just the direction that I'm applying KVL and summing up the voltages. Some techniques take all the voltage sources and put it on one side, and then take all the passive components and put it on the other side of the equation. So you would get VA equals, VR2 plus VR3 instead of summing it up to 0. Does that make sense?
Yeah.
Okay. So the point I was trying to make, let's see, was if I3 and I2 were the opposite direction, then my voltage polarities would be in the same direction. So instead of being minus I3 R2, it would be plus I3 R2 here and here. Okay. But it would balance out because when we write equations for mesh 2 and mesh 3, those would flip. Those equations would flip. So we would still end up with the right answer. Okay, let's stop right here. I think we are over time by about a minute and a half. Quiz on Mondays, as usual. The topic will be node voltage analysis. Homework has been assigned. I'll make it due like Sunday night. If you have any questions, I'll be in my office. I'll be available over the weekend also. So send me an email. I can meet you via Zoom if you have a question. And then mesh current analysis has been introduced. Open up the homework, take a look at it. I will go over the theory again after quiz on Mondays, and then we'll do an example and finish it up on Wednesday. Homework for mesh current analysis would be due sometime next Thursday or Friday. So again, get started on it. You might not be able to go through much of it right now, but again, consider it being assigned. All right, I'll wish you a good weekend, and I'll see you all on Monday.
Professor,
Yes.
I just realized I never submitted my work for homework 8. I just submitted it. Is there